Hello, I'm Yeong-Do Park. My speech today addresses a study on surface defects with electrode misalignments in resistance spot welding of hot stamping steels. I also would like to acknowledge the contribution from my students Young-Gon Baek, Woo Sung-jin, Anju Lee, and Arun Alachan. There has been quite of surface defects has been reported or introduced in regions about welding from the industry or researchers. One of the popular one is the surface expression, which is also called known as a marathon. After the regions about welding, weld surface has this kind of a marathon form, like in this figure. The other popular surface defects is surface crack, well known as a liquid metal invertment. The cracks can be seen from the weld surface, which is also penetrating through the thickness of the weld. Today's my talk will only focus on this marathon surface expression. So first of all, what is the marathon in rigid spot welding? If you look at the car body rigid spot weldment very carefully, you can easily be able to find this kind of surface expression, uh, the marathon. Yeah, when we look at this surface defects very carefully, this kind of a marathon was formed from the edge of the regions of weld, and if you cross-sectioned it, it looks like this marathon thorn was originated from the inside of the molten weld nugget. Were is this a defect? Yes, it is. It has some issues with the surface appearance at the exposed area of cavity, and also it has some safety issues for the, the line worker. And also it may provide inconsistent weld quality, and also most importantly, additional cost for the grinding work. So I tried to look at any reports from the earlier literature, and I was able to find a couple of reports from the several conferences. The Subaru actually reported this kind of overmelt, which is also same with the marathon, and when they applied this one-side spot welding technology. And also, year 2015 Euro Car Body Conference, this Opel Astra, I took some image of the weld, and it had this kind of marathon formed in the resistant weld surface. And also, our internal study also showed that when we make the very short pitch resistant weld, there is a large marathon can be formed as well. So this kind of marathon issues has been known or reported from quite for a long time, and I tried to look at or investigate these issues with some more industrial perspective. There has been a possible scenario of the marathon formation. When I talked with the industry, they are telling that marathon has been observed with electroangular misalignment due to the limited access of the robot. And secondly, the shunting effect can cause also the marathon. Especially, as I mentioned, this kind of short pitch weld makes the high shunted current, which makes the very high temperature at the edge of the uh, weld. And also, as Subaru mentioned, that single side RSW may also cause this kind of a marathon. So if you look at the cross-section image, this when you have a previous weld, and then after that the shunted weld will have a high possibility of having a marathon. So localized surface melting possibly due to the high current density or poor cooling could be the reason. This kind of a surface melting by localized high temperature at near surface can be occurred or along with related with the material properties and process characteristics. In case of material properties, high bulk resistance or aluminum silicon coated hot stamping steel or special sheet combination or poor thermal conductivity can also bring the very high temperature on the surface. And in terms of process characteristics, as I mentioned, the electrode misalignment, electrode degradation, or shunting, or gap, or very high heat input may also cause the very localized high temperature at the near surfaces. And our research investigation mainly focus on this aluminum silicon coated high stamping steels with electrode misalignments. In many cases, this kind of marathon were observed with resistance spot welding of aluminum silicon coated hot stamp steels, which is also known as the commercial name of Uzibor. And it has 1.5 gigapascal grade after the hot stamping condition. This image shows the hot stamp after the hot stamping. There has been several oxides and also intermetallic compound has been developed. Most outer side is aluminum oxide. Alumina can be formed, and in the middle there has several different types of aluminum, iron, and silicon complex metallic compound can be formed. This kind of aluminum oxide layer and intermetallics actually can be the source of the very high resistance. So when you make the resistance by welding of the aluminum silicon coated hot stamp steel, the surface heat generation is very high due to this aluminum silicon coatings. So I tried to look at any earlier investigation about the contact resistance of these aluminum silicon coated hot stamp steels, the static resistance. I found there's one quite interesting research from Waterloo University at the year 2017. They actually measured the static resistance among all different types of coatings, aluminum silicon as received or aluminum silicon hot stamps. So this aluminum silicon hot stamp steels are our interest, and the result shows that aluminum silicon hot stamp steel actually has the 3 times higher static resistance or contact resistance than the zinc coated steel. So this 3 times higher resistance may result in the very high and rapid heat generation. Because of this kind of very high contact resistance at the aluminum silicon coated hot stamping steels, when you make the weld with the aluminum silicon hot stamping steels, there has been a large high temperature development at the paying interface. At the same time, the interface between the electrode to the sheet surface are quite large at the initial weld time. Because of this high temperature development from the surface, at the end of the weld time, this weld nugget shape is very edge of the fusion line is very close to the surface of the metal. And otherwise, the other hand, in case of general zinc coated steels, I don't have an image with the initial weld time, but if you look at the end of the weld time, the nugget shape is more close to the oval shape, and the fusion boundary is quite far from the steel sheet surface. So this result also proves that the aluminum silicon hot stamp steel because of the high contact distance, there is a quite large temperature development from the surface. The objective of this research was investigating the mechanism in the formation of marathon due to the electrode angular misalignment on the aluminum silicon coated hot stamping steels. Also, secondly, to suggest a solution to suppress the marathon with the current profile of the resin spot welding uh, welded with aluminum silicon coated hot stamp steel, such like pulsing schedules with upslope. Were to make a systematic observation, the interrupted test with welding time has been attempted with the 4-degree electrode misalignment. At the 83 milliseconds, small marathon is observed, and at the 267 millisecond, very large marathon can be observed. And this marathon looks like molten metal is expelled out from the growing nugget. We try to correlate with this power or voltage signal with welding time, and at the first drop in power or voltage is reason of the very small marathon forming at the surface expression, and at the second very large voltage drop is actually the reason of the large molten metal expelled out from the weld nugget, which result in the very large voltage drops. At the same time, the distance from the fusion line and steel sheet surface has been measured. And with welding time, it is getting lower, smaller, and smaller, which means that the surface temperature was very high. So several voltage drops suggest the surface expulsion or molten metal expel from the nugget occurs more than one time. The temperature development was simulated by using the commercial software SimUpact. From this SimUpact simulation, you can actually be able to see the very large temperature development. And at the end, actually, marathon can be formed and molten metal can be expelled out from there. In the captured image, you can clearly see there is a very high temperature development at close to the sheet surface, and then actually because of the poor cooling, at the 82nd millisecond, surface melting is actually start to occur, and here molten metal expel can be also observed proved by the simulation results. From the simulation result, simulation data has been plotted for the contact area for 6-degree tilting and 0-degree tilting, and it shows the 6-degree tilting has a very less contact area, and because of this poor contact, the cooling effect has been diminished at the local area. So with the welding time for the 6-degree tilting angle, the surface temperature actually over the steel melting temperature. But however, the 0-degree tilting it shows the less than surface steel melting temperature. So we try to use the IR camera to make the actual temperature measurement from the weld, and this is the image of the electrode, and we measured right underneath the electrode and also steel contact area. And at 0-degree C, temperature only develop up to the 800, 900 degrees Celsius on the surface. But at 2 degree, it gets higher. And 4 degree, it's very close to the 1400 degrees Celsius. And then at 6 degree misalignment angle, it shows the very close to the melting temperature of the steel sand, which is the actual experimental measurement, direct evidence for the surface melting. To summarize the mechanism of marathon formation with the increase of welding time, the total process can be divided into the 3 steps. In step 1, electrode angular misalignment and poor electrode contact, and because of that, the poor cooling. In the second step, with welding time, the tilted nugget growth can be occur, and also very high temperature, surface temperature rises to the very high temperature. And then at the last stage, step 3, steel surface start to melt and expel out of the molten metal from the nugget. It ends up with the metal at the weld surface. From here, I'd like to talk about the suppression of the metal in resistance welding. Based on the mechanism of the formation of a metal, the governing factors are the electrode angular misalignment and poor contact. So it is not feasible to improve the electrode angular misalignment considering the automated and complex production condition in car body. This is the brief schematic diagram with the increase of electrode misalignment with the welding current. This is the weldable current range without the electrode tilting. However, with the increase of degree of electrode misalignment, the welding current, limited by this metal tone and this red dotted line. So in low current only can be applied with no metal to have no metal tone. However, it brings the small nugget. So low current may reduce the formation of metal tone, but small nugget raised another weld quality issues, and also suggests to improve the contact between the electrode and steel surface using current profile. Therefore, the issue is how to improve the contact and also the cooling at the beginning of the early stage of the weld. K.C. Wu first actually reported the effect of the upslope at the year 1975 on expression in resistance spot welding. So as you can see from this schematic diagram, at initial stage of the weld current profile, when upslope is adopted, actually a very low initial current in conjunction with the slow rate of upslope heating actually improves the microscopic contact area. So the welding current is increased only after the contact area will have increased by the gradual plastic deformation and melting. So the contact will be improved and the cooling effect from the electrode can be improved with his theory. Were to confirm his theory and check whether it is working also work with the surface melting behavior, various upslope time has been applied with a different misalignment angle of 2, 4, and 6 degrees respectively. By applying this different upslope cycle at 2 degree, at 4 cycle, metal tone was actually diminished. At 4 degree misalignment angle, 10 cycle of the upslope provided no metal tone free weldment. And 6 degree, actually 12 cycles of upslope was required to have metal tone free weldments. So the result shows that it actually upslope actually works and it actually improves the contact for the condition of misalignment tilting angle. We'll try to explain the mechanism of suppression of metal tone with the application of this upslope current profile. It has been divided into the 3 steps. At the step 1, there is electrode angular misalignment and poor electrode contact at the beginning. But during the upslope welding time, in step which is corresponding to the step 2, very slow heating and improve the contact area with high temperature plastic deformation and ends up with the improved cooling condition. And later stage of the welding, step 3, the nugget growth without high heat generation on the surface, and it only shows the small plastic deformation traces. In here, I'd like to explain the mechanism of suppression of metal thrown during the welding. At the beginning of the weld, there is an electrode angular misalignment and poor electrode contact. However, with the application of upslope in step 2, the slow heating and improved contact area, which results in the improved cooling. And at the end of the welding stage, the step 3, nugget growth without high heat generation on the surface. Therefore, no free of the metal thrown can be achieved after the weld. Along with the previous result, this kind of process map can be achieved with the increase of electrode angle and how much upslope time is needed. And this red line is actually boundary condition where minimum upslope is required, cycle is required for each 2-degree misalignment angle. At 4-degree misalignment angle, you need at least 10 cycle of upslope time, welding time, and 6-degree of the electrode misalignment, you need at least 12 cycles of the upslope times. So in here, this process map, lower downside is presence of the surface defects such as the metal thrown with the limited upslope time. And with the longer upslope time, this area stands for the absence of the surface defects, the metal thrown. So this process map can be very useful to prevent or utilize in the actual car body production line. With that, I'd like to conclude following conclusions. Electrode angular misalignment or shunt effect can cause the metal thrown formation with localized surface melting, followed by the molten metal expelled out from the inside nugget. Based on the mechanism of the formation of the metal thrown, the governing factors are electrode angular misalignment and poor contact. Therefore, a low initial current in conjunction with the slow rate of upslope heating improves the microscopic contact areas during the resistance for welding. And finally, the welding current is increased only after the contact area have increased by gradual plastic deformation and melting. With that, thank you very much, and I'd like to welcome all the questions. Thank you.